All right, today we're putting on our detective hats. We've got a physics mystery on our hands involving a particle on the move, and our mission, should we choose to accept it, is to figure out exactly when it stops, where it stops, and what's happening to it at that very moment. Welcome to the case of the stationary particle, where our number one tool is going to be calculus.
So, here it is. This is our main clue. This equation right here describes the particle's position, which we're calling x, at any time t. Our job is to find the time, the position, and acceleration when its velocity hits 0. I know, that equation might look a little scary at first glance, but don't worry, we're going to break this whole thing down together, one step at a time.
Okay, before we even touch those numbers, let's ask the most basic question. What does it actually mean for a particle to stop? Well, in the world of physics, the answer is actually really simple and clean. It means its velocity is 0, nada, zilch. For that one split second, it's not moving. And that idea right there, that's the key to this whole case.
So how in the world do we find velocity if all we have is an equation for position? Well, this is where calculus becomes our secret weapon. See, velocity is just the fancy term for the rate of change of position. And the tool we use to find that exact instantaneous rate of change is the derivative. It's literally the key that unlocks the velocity that's hiding inside our position equation.
So, our first real step in this investigation is to take that position equation and find its derivative. This process is called differentiation, and it's going to morph our position formula into a brand new velocity formula. This will be our next major clue. Let's do it.
Now this part is way easier than it sounds. You just follow a simple recipe called the power rule for each little piece. For t cubed, the 3 just hops down to the front, and we lower the exponent by 1, giving us 3t squared. For negative 12t squared, we multiply the 2 by negative 12 to get negative 24t. For 36t, well, that just becomes 36. And any lonely number, a constant like 30, its derivative is always 0. Poof, it's gone.
And bam! Just like that, we've uncovered our first major piece of evidence. By taking the derivative, we found the particle's velocity equation. This formula tells us the particle's speed and direction at any given moment. This is a huge leap forward in solving our mystery.
Okay, let's bring it back to the mission. We need to know when the particle stops. And since we've established that stop just means velocity is 0, the next question is pretty obvious, right? At what time t does our shiny new velocity equation equal 0?
To get that answer, we just take our velocity equation and set the whole thing equal to 0. This gives us what's called a quadratic equation. So for a minute, we can put our physics detective hats aside and put on our algebra hats. The goal now is simple. Solve this thing for t.
Let's break this down. First thing I see is that every single one of these terms can be divided by 3. So let's pull that 3 out front to make things easier. That leaves us with t squared minus 8t plus 12 equals 0. Ah, much better. Now we just need to find two numbers that multiply to positive 12 but add up to negative 8. And, yep, that's got to be negative 2 and negative 6.
And whoa, look at this. This is a major twist in the case. We don't just have one solution, we have two. For that whole equation to be 0, either the t minus 2 part has to be 0, or the t minus 6 part has to be 0. And that tells us something incredible. Our particle doesn't just stop once. It stops at t equals 2 seconds, and then it stops again at t equals 6 seconds. How cool is that?
Okay, we've officially nailed down the when. We have the exact times the particle is at a standstill. But we're not done yet. The next logical question is where? Where exactly was the particle when the clock hit 2 seconds, and where was it at 6 seconds?
To find the where, we have to rewind and go all the way back to our original piece of evidence, that first position equation. It's actually pretty simple from here. We just take our two time values, 2 and 6, and plug them back into that equation one at a time to see what position x we get.
So, we run the numbers, and here's what we find. At 2 seconds, the particle stops way out at a position of 62 feet. But later, at the 6-second mark, it is stopped back at the 30-foot mark. So now we have a story. The particle moved out, stopped, turned around, and then stopped again. The plot thickens.
So we've got the when and the where, but there's one last crucial clue to uncover: acceleration. Now here's a common trap. You might think, hey, if it stopped, velocity is 0, so acceleration must be 0 too, right? Nope, not necessarily. Just think about tossing a ball into the air. At the very tippy top of its flight, its velocity is 0 for an instant, but gravity is absolutely still accelerating it downward.
And there's a really cool symmetry here. Just like velocity is the derivative of position, acceleration is the derivative of velocity. It just tells us how fast the velocity itself is changing. So to find our acceleration equation, we're going to do the exact same thing we did before. Take the derivative, but this time we'll do it to our velocity equation.
We take our velocity equation that we found, and we apply that same power rule all over again. The derivative of 3t squared becomes 6t. The derivative of negative 24t is just negative 24. And that constant, 36, just like before, it vanishes. See, it's the same simple process.
And there it is, the last tool we need to solve this thing. Our acceleration equation is a equals 6t minus 24. With this in hand, we can now calculate the particle's acceleration at any time we want, especially at those 2 moments it was stopped.
All right, let's plug in our 2 times. At 2 seconds, the acceleration is negative 12 feet per second squared. That negative sign is key. It means it's being pushed in the negative direction. But then, at 6 seconds, we get a positive 12 feet per second squared. It's now being pushed in the positive direction. And check that out, it's the exact same amount of acceleration, just in opposite directions. So let's lay out all the evidence. Case closed. Here is the final report, all in one place. We found that the particle stops first at 2 seconds, located at 62 feet, while accelerating at negative 12 feet per second squared. It stops a second time at 6 seconds, this time at the 30-foot mark, while accelerating at a positive 12. Every piece of the puzzle fits.
At the end of the day, this whole exercise isn't just about some imaginary particle. It's about showing you just how powerful this one idea, the derivative, really is. It's the key that lets us move from knowing where something is to how fast it's moving, and finally to how its movement is changing.
And that brings us to one last thing to chew on. We saw the particle stop twice, but with those equal and opposite accelerations. So think about this. What does that tell you about what the particle is just about to do in the instant right after it stops at each of those points? That little negative and positive sign, that's the clue to its entire journey. Something to think about until next time. Thanks for joining the investigation.